We're going to continue our discussion of Faraday's law with talking about ideal transformers today. An ideal transformer has two or more, I suppose. You can have more than two coils of wire that share the same flux. The way this works in practice is you have some sort of high permeability, remember that's mu, high mu ferrite material core that you wind your coils of wire on. So it might look like this, and I'm sort of drawing a copy of a figure that I have on the handout. So you might have coil number 1 going around here, and coil number 2 going around here like that. So we've got N1 turns on coil number 1, and we've got N2 turns on coil 2. And this one is going to have V1, and this one is going to have V2. But because these are wound around this high permeability core, the flux going through one loop of coil 1 is equal to the flux going through one loop of coil 2, or one turn of coil 2. And as a result, if we write Faraday's law for both sides, we can say that there's just one common flux variable phi that is equal to phi1, which is equal to phi2. So then when we do write Faraday's law for both sides, we can have that V1 is going to be minus N1 d phi1 dt, right? That's Faraday's law. Which is minus N1 d phi dt, because we just said that those two things are equal. And we can also write down a similar Faraday's law expression for the voltage in coil 2. So the voltage across coil 2 is going to be minus N2 d phi dt. Now take a look at that. We have the same time derivative of the flux in both of these equations. So we end up with V2 over N2 is equal to minus d phi dt, which is also equal to V1 over N1. The voltages in these coils are proportional to each other. V1 over V2 is equal to N1 over N2. That's how an ideal transformer works. So in an ideal lossless transformer, all the power that's delivered to the primary coil has to be delivered to the load on the secondary coil, because there's nowhere else for the power to go. So if the power going into coil 1 is going to be V1 times I1, as it usually is, or if we're in phasor domain, which we could be, it's going to be 1/2 the real part, but we're just going to stay in time domain for now, right? We end up with the same answer either way. And if we're delivering any power to coil number 2, then that power is going to have to be V2 I2. And we know that V1 and V2 have this relationship, and we also know that P1 and P2 are related to each other, are equal to each other. Then we have that power 1 is equal to V1 I1, which is equal to power 2, which is equal to V2 I2. But then V2 is just V1 times N2 over N1, which means V1 I1 is equal to V1 N2 over N1 I2. Cancel out the V1s, and we see that, whoops, I1 over I2 is N2 over N1. So the currents are also proportional, but they have the opposite proportionality. So I1 1 over 2 for currents is equal to N2 over N1, where V1 over V2 is N1 over N2. It's easy to get those swapped. So I'm writing them next to each other so you can notice the difference in those two expressions. So if I've assumed that there is some sort of load on coil number 2, let me redraw my picture in a slightly more cartoony and less beautiful way here. If I've assumed that there is a load on coil number 2, like that, and I have this relationship between the currents and the voltages, when I apply some source, or if I'm looking into coil number 1 here, there is some input impedance, which is just V1 over I1, but that depends on what is the load that's attached to coil number 2. And I'll show you how that works. Now I said that V1 over I1, I said that V1 over V2 is N1 over N2, and I1 over I2 is N2 over N1. Now we also have the fact, based on Ohm's law, that V2 is I2R. So let's write those things in terms of V1 now, and I1. V2 becomes V1 times N2 over N1. And I2 becomes I1 times N1 over N2. And then we still have R coming down from that equation. Which means if I want V1 over I1 to figure out what the input impedance is here, divide through by I1. Get rid of that I1 in that equation right there. Move this N1 over N2 to the other side, N2 over N1 to the other side, and you get that the input impedance looking into coil number 1 is N1 over N2 squared times R. So that's interesting. Because of this proportional relationship between the voltages, where V1 over V2 is N1 over N2, and the proportional relationship between the currents, where I1 over I2 is N2 over N1, we end up with this impedance transformation happening where the ratio of the number of turns becomes a multiplicative factor on the input impedance. In my next videos, I'm going to do a couple of examples with transformers, but this one just explains the theory.